Okay, so for chapter 26, this is the outline. So we will define what is current and the current density. So current is a scalar, although a current should have a direction, but current is not a vector, it's a scalar. And current density is a vector field. And then we'll also introduce what is a resistance, like how we define the capacitor. So this is another fundamental circuit component. And then we'll talk about the Ohm's law. So I suppose even in high school physics, you have already learned what is Ohm's law. And yeah, we will briefly introduce a power, semiconductor, and superconductor. So of course, we will not teach how to calculate the semiconductor circuit, because it is the knowledge for specifically the ECE student. Yeah, they will learn something like applied electronics for the semiconductor circuit. Yeah, of course, superconductor circuit, even ECE student will not learn about it. So it's more advanced topic. Okay, so here we will introduce current, electric current. So any isolated conducting loop, regardless of whether it has excess charge, is at all the same potential. So yeah, so which means that, so if suppose this ring is formed with conductor, and in chapter 23 we already mentioned that inside the conductor there won't be any E field. So if there is no E field inside, then there won't be any potential difference. There won't be. So for the whole loop, the electric potential should be the same. So there won't be any potential difference between any 2 points inside the conductor. Okay, so whether regardless of whether it has excess charge, so with or without charges on the loop, it doesn't really matter. The potential should still be the same. So no electric field can exist within it or along its surface. So if you can remember, the E field and the potential should have something like the relationship would be like E equals the negative of the gradient of the potential, or the other way around, it would be like V equals negative integration of E dot ds for a path. So as much as there is no E, then the potential difference will be 0. Okay. So next, so if we insert a battery in the loop, the conducting loop is no longer a single potential. Electric field acts inside the material makes up the loop, so exerting force on the internal charges, causing them to move and thus establish a current. So I think all of you should know what is a battery. So if you put a battery here, and then this is the conductor connecting the two terminal of a battery, then it will be different from this case. There will be potential difference across here. So there will also be current. And actually, I think you should know that the direction of the current is opposite to the direction of the electron, as much as if you have learned chemistry. So yeah, so that's this is the direction of the current from the positive terminal to the negative terminal, and practically the moving charges should be electron rather than a positive ion rather than that. So actually what is really moving is the electron. So actually the direction of the electron should be the other way around from the current. But when the circuit theory established, the physician or the scientist does not know the moving particle is the electron yet. So at that time, they define the direction of the current like this. And yeah, even though they find electron later, maybe like tens, multiple decades later, they find the electron. But yeah, after that, they don't try to change the direction because yeah, many theory have already established. So correcting it will be a tedious work to do. So they just keep the direction of the current there. So yeah. So this is the mathematical definition of the current. So current is like dq dt. Take the derivative of the charge with respect to time. So yeah. So as much as the charge amount is changing, then yeah, this value is not zero. Then yeah, it defines the current. So it is the change of the charge in unit time. Okay, so I think so far is easy. So next, here it mentioned this one is called the KCL, Kirchhoff current law. So this is one of the two Kirchhoff law. One is called KCL and another one called KVL. So the other one should call Kirchhoff voltage law. Okay, so in this chapter I think we only maybe in the previous chapter we already mentioned the KVL a bit. Yeah. So when we talk about the series capacitance, we somehow use the Kirchhoff voltage law there. So when we consider a loop, then yeah, so the potential change will be a zero for a complete loop. So here is it's a duality. So here when we consider, so this one we have several lines. So this is 1, 2, 3 connecting at this point. So here it tells you that suppose this is the current I0, I1 and I2. So Kirchhoff current law tells you that the total current going into a loop should be the total current going out from the loop, which means that in this figure we can write it as I0 equals I1 plus I2, like this. Okay, so if there are more lines connecting to the same loop, then yeah, there will be more term. But but simply speaking, it is something like no, not there. So the current going into the junction must equal the current going out. But usually I will not use it like this. Usually I will consider usually I will define for example all the current going out, and then I will just consider all the current going out will be zero. So actually it will be the same, because you can define the I0 is going in or going out. So whenever I try to use this, usually I would just define all the current are going out or all the current going in, and then they sum up to be zero. Then it will makes you have less chance to make mistake, because suppose some of the current going in or some of the current going out, then you need to distinguish maybe which one is positive or negative. So you can make mistake on the plus or minus sign. Then you may make mistake like this. But usually I would just define all the current going in or all the current going out, and then they sum up to zero. Then it makes you have less chance to make mistakes. Okay, so next we talk about the current density. So it's like a physics stuff, not circuit stuff. So when we talk about circuit theory, then usually we only consider the voltage, the current. We don't want to talk about the density because it's a vector. And circuit circuit designer don't like the vector stuff because it is difficult to calculate. So so circuit theory try to simplify the variable down to some scalar variable, and then it makes things easier to calculate. But here this is a physics course, so we still need to talk about some fundamental definition like the current density. And actually this definition is not like the usual definition, because usually for definition of a variable, usually it will be like a variable equals to something else. But here the definition of J, the current density J, is put on the right side and actually is inside a surface integral. And then it tells you that the current equals the surface integral of the current density dot the area vector, the differential area vector. Okay, so this is a surface integral, not a closed surface integral, but it is for a arbitrary surface, not necessarily closed. So we don't have a circle here. Okay, so and actually. So what we need to know is that current is a vector. It's called J, and the SI unit should be ampere per meter. And of course, the SI unit for the current is A, ampere. Ampere. Okay, so this is A. And then this is the SI unit for J, and then times this is area, should be meter square. So you can quickly find that the SI unit for J is A over meter square, which should be like this. Okay, so so here it says the dA is a vector perpendicular to the surface element of the area dA, and the integral is taken over any surface cutting across the conductor. Just say for this one. So it is like a wire, and so maybe you can define the surface is something like this, cutting across there. So you're integrating over this surface. So of course it is just a cross section, so I only draw a line here, but maybe it should be a surface, or maybe you can just cut it like this. So this is a two-dimensional. So maybe if I just cut the wire like this, then so this surface is bounded by this path, and then by this contour. So and then maybe you can just integrating the J dot dA over the whole surface, and then you will get the current going through this wire. Okay, so the same direction as the velocity of a moving charge if they are positive charge, and the opposite direction if the So here, of course, you need to define what is the direction of dA. So for example, if you just define dA pointing to the right side, then if it is a positive current, then the current is going to the right side, and the other way around. So and vice versa, I mean. So so this is not so. Yes, I think it's easy to understand. So. Okay, so here we talk about something like hardcore physics. So it tried to go in deep in a microscope way to talk about what is current, what is the velocity of the charge. So here it says we have conduction electron are actually moving to the right, but the conventional current is said to be moved to the left. So in this figure, we assume that the current is moving to the left side, and then yeah. So you can consider if it is positive charge, then the positive charge should move from right to left. And if it is negative charge, it should move from left to right. So for this one, it doesn't really matter that whether it's a positive charge moving to the left or negative charge moving to the right. So for this one only, so yeah, it doesn't really matter. But in chapter 28, when we consider something called Hall effect, then yeah, so it is the experiment tells you that the moving particle should be negative charge rather than positive charge. If it is positive charge, there will be some contradiction. So but for here, positive charge or negative charge will give you the same conclusion. So in this case, it doesn't really matter. Okay, so here we just assume it is positive charge moving to the left. So here we assume the velocity of the charge is Vd, or maybe the average velocity is Vd. And in that case, we can imagine there is a E field pointing to the left side. Imagine there is a E field pointing to the left side. So this E field will push the positive charge to the left side. Yeah, because for positive charge, the Coulomb's force should have the same direction as the E field. So here you can assume there is a positive charge moving to the pointing to the left side, or you can imagine it is generated by a battery like this. You can imagine like this. If we have a battery Vs like this, it will generate a current going counterclockwise. Okay, so suppose we have I pointing to the left side, and also J should also point to the left side. And in this case, we just assume the current density is uniform across any cross section. So J is uniform across any perpendicular cross section to the Y. Okay, so here we can write some identity like Q equals something times the E. This is the elementary charge. So this is elementary charge. So we here try to calculate how many electrons are there, or how many positive charge are there, and we just assume this is a positive elementary charge. So here we try to calculate how many there is. So A is the cross-section area. So cross-section area, and then this is the length. So when we have the cross-section area A here, and then multiply by the L, the length of this segment, then it will be the volume of this cylinder. I mean cylinder. Okay. So yeah, so this is the volume. This is the volume. And then this N is called the density, the charge density. And of course, this is a volume density. So this is the volume density times the volume. So it is how many charge in this volume, and then multiply by the elementary charge amount. So this is the charge amount in this part. Okay, so so here we have another equation like this is the time it takes charge go from here to here. And then L equals Vd. This is the length divided by the average velocity, will be the time a charge it takes to go from this point to that point. Okay, so this is the time it traveled. And then, so here we have I equals Q over T. I equals Q over T. So here we have Q, we have T. Of course, the original definition for the current is like I equals dq dt. So here you can imagine this Q is a delta Q, this is a delta T. Then it makes things correct. So you can regard it as, but of course I don't try to rewrite that because yeah, I need to add it here and also add it here. But it may, yeah, make some equation not so correct. So ouch. Oi. 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 Hey. Okay. So we just plug in Q and T into here. So we have NaL times E on the top, and then here T equals L over Vd here. So here we can just cancel this L and this L. And then we have Ne putting in the front, and then A times Vd. Yeah, so N times E times A times Vd here. Okay, so yeah. So we have I equals this expression. And then finally, we have J equals JA, because originally it is like I equals integration of J dot dA. So if J is perpendicular or parallel to dA, and also J is uniform, then it is just like a multiplication, J times the cross-section area. So it's just like integrating a constant, which is nothing but a multiplication. So we have I equals JA, so I over A equals J. So we have I over A, so I just move this A over. So I over A is J, and then we have NE times Vd. So this is what we want to derive. So it tells you that the J, the current density, is proportional to the velocity of the charge. Of course, here E is a constant. E is elementary charge. It should always be 1.6 times 10 to the minus 19 coulomb. And for this charge density, it is also a constant for a specific conductor. So for a specific conductor, this is also a constant. Of course, if you change it from just say a copper to silver, then this N will change. But suppose this is a fixed material, then this whole term should be a constant. And then it tells you that the current density is proportional to the velocity of the charge. Okay, so yeah, so here it's just call it the drift velocity. So call it Vd. Okay, so here it says the product Ne is the carrier charge density. Okay, it's the current charge density. Okay, so we just would like to derive this equation. Okay, so here let's take a look at a sample problem to slightly familiar with how to calculate the current density. So here it says the current density in a cylindrical wire of radius R, capital R, is uniform across the cross section of the wire and is J. So what is the current through the outer portion of the wire between the radial distance R/2 to capital R? So here we only like to calculate the current at this part. Like this. Okay, so here, as much as the J is uniform, then yeah, we just need to use multiplication rather than integration. But for part B, we really need to use the integration. So here we only need to calculate the area for the ring A prime, so which is the area of the ring, ring. Yeah, so A prime would be, so the whole radius is pi r squared, and then for the inner part it is also another square, so we just need to subtract this one out, so it is a minus pi times R/2 quantity squared. So this is nothing but 3 pi r squared over 4. Okay, so we can just plug in the number. 3 times 3.14 times R is 2 millimeter. So this is 2 times 10 to minus 3, and then square, and then all over 4. So this number is 9.42 times 10 to minus 6 meter square. But in this case, I do not really suggest to write it as a 9.42 micrometer square, because there is an ambiguous, like whether it is mu m times mu m, or whether it is 10 to minus 6 meter square. So I do not really suggest you to write it as this way. I do not suggest it to. Yeah. So I just write it as times 10 to minus 6 meter square. Okay, so next I equals J times A prime. Okay, J is given here, so J is 2 times 10 to the 5th power, and then times 9.42 times 10 to minus 6. Okay, so it is 1.9 ampere. So this is the answer for part A, and I think it should be quite easy. So it only will involve some multiplication. Okay, so next, here we talk about so here for part B, suppose instead the current density through the cross section varies with radial distance R as J equals AR squared. So it is not uniform. Now it's related to the radius or the distance of the ring to the center. Okay, so in which A is this value and R is in meters. So what now is the current through the same outer portion of the wire? Okay, so here we really need to calculate the surface integral J dot dA, or actually like this. But yeah, at least we can quickly know that J is parallel to dA, so we can quickly write it as an integration of J times dA. And then we try to plug in J. This J is this J. So we have integration of, or I can just I can just make it like this. So J is actually AR squared. And yeah, so actually this is a polar coordinate. This is a polar coordinate. So this is our axis, and then there is another thing like theta. So it will be something like, so dA here will be like, dA will be r d theta, like this. If you can't really remember, then you can imagine the polar coordinate will be something like this. So suppose this is dA, this is dA, this is dA. So and this is r, this is theta, and this angle is d theta. So if dr and also this is dr, so if dr and d theta is small enough, you can regard this one is a rectangle, although it is not. But yeah, if dr and d theta is small enough, you can regard this one is a rectangle. And the area of this rectangle is like this side is dr, so no problem. And for this one will be r times d theta. So in high school mathematics, you should know this is the radius times the angle in radian. So r times d theta is this side. So dA will be r times dr d theta, like this. Okay, so here we have a dA equals r times dr times d theta. And here, suppose we need to integrate, we need to dr d theta, so we need to determine the lower and upper bound. So for dr, rather than calculating for the whole circle, we just count it from r over 2 to r. So the lower bound and upper bound should be r over 2 and r respectively. And for the theta, we actually go over the whole circle for the theta. So this is theta. We actually go from 0 degree 0 to 2 pi for the complete ring. So it should be like 0 to 2 pi for d theta. Okay, so here a is a constant, so we can put it out, and then we have dr. So integrating dr, so let's count. We have r squared and r. So altogether we have r cubed, and we integrate it from r over 2 to r. And then the remaining one is d theta. And then from 0 to 2 pi. Yeah, actually we can just write it like this. If you are not so comfortable, you can just write it as integrating 1 dot times d theta from 0 to 2 pi. Then yeah. Usually I just write like this. So yeah, so this double integral is simply like this. Yeah, so some of the case, yeah, especially in mathematical class, the double integral may not be so easy. For example, if it is like integration dx dy, and then you cannot factoring like this is a function of x, this is a function of y, then you cannot do this stuff. For example, if it is like x squared plus xy plus y squared, then you need to do it one by one. Then you need to do it one by one. Or for example, if it is like 0 to 1, 0 to 2, then you need to regard y is a constant, and you integrate for x first, and then yeah, and then you try to plug in a 0 and 1, and then the x will vanish, and then you do the same thing for y, yeah, step by step. But here, suppose the function can be factorizable. So r and theta can be isolated. Then yeah, so this is a function of r, this is a function of theta. So and of course this function of theta is constant 1. So yeah, so here the integration is easy. Here we have a times integrating r cubed will be r to the 4th power over 4. r to the fourth power over 4. And then we evaluate from r over 2 to r. And then this is nothing but theta. And then we evaluate from 0 to 2 pi, which is 2 pi. So this is a times r to the fourth power over 4 minus r over 2 quantity to the fourth power over 4, and then times 2 pi. And then we just need to plug in the number, or maybe we can just simplify first. It is like 15 over 32 a times r to the fourth power times pi. Okay, so this is just an algebraic calculation. Okay, so 15 over 32 times a is this number, 3 times 10 to the 11 power, and then times r is still 2 millimeter square. So this is 2 times 10 to the minus third power, and then times actually this is the fourth power, and then times 3.14, and this number is 7.18. Okay. Any question for it? So this sample problem just let you familiar with how to actually use the definition to calculate the current from the current density. And yeah, of course the current density here is not uniform over the radius. So yeah, so it requires some integration. But hopefully this is not so difficult, because at least this density is not related to theta. If it also related to theta, then the integration will be more difficult to calculate. Okay, so next we have another sample problem. So here it asks you what is the drift speed or drift velocity of the speed is a scalar, velocity is a vector. So so the conducting electron in a copper wire with radius r equals 900 micrometer, so which is quite thin. So where it has a uniform current I. Assume that each copper atom contribute one conduction electron to the current, and the current density is uniform across the Y cross section. Okay, so this is so this requires some constant, like in the chemistry class. Of course I don't really remember that, but anyway, so it's just a simple calculation to make use of the equation we just derived. So J equals NE times VD. So to let you have some numerical sense, because for I think for engineering student the most important thing is that you need to have some numerical sense. You need to know whether this number is large or small for different situation. Even though you don't always come up with a correct or accurate value, but you should have some sense that whether this number is large or small in mind. Okay, so here it says so we try to calculate the drift velocity or drift speed. Okay, so here we have the expression like this is the N is the atom per unit volume, and then this atom per mole. So this is like the charge density. So how many atom per unit volume? And so it is like you just plug in something. So here we have atom per mole. This number we can just check it from the appendix. So we have this atom per mole, So if we just divide atom per mole here, then we need to multiply 1. So here we have moles per unit mass. So it's like the mass density, So we can also have this number in the appendix. So here we divide the mass, so we multiply the mass. So mass per volt. So actually this is the density. This is the mole per mass. This is the mole per mass. Okay, so we have 3 numbers which can be checked from the appendix. Or actually this is the Avogadro numbers. So when you learn chemistry in high school, so you should know this 6.02 times 10 to the 23rd per mole. Okay. So actually this is atom per mole is actually this number. And then mole per mass. So it is the reciprocal of 1 over m. So yeah, we can have mass, molar mass of a copper. So as much as we have so many atoms of the copper, the mass will be this number. Okay, so the remaining stuff is just to plug in all the values here. So we have a 6.02 times 10 to the 23rd power, and then times 1 over this is m. But we actually need to change it to SI unit. So this is gram. So we need to times 10 to minus 3rd power to make it like kilogram per mole. And then times molar mass. This is mass per volume. This is the density. And yeah, so this is like 8.96. But actually we need to change it to a kilogram per meter cube. Okay, so when we change G to kg, we need to divide by times 1 over 10 to the 3rd power. And when we try to change this per centimeter cube to meter cube, so 1 meter is 100 centimeter. So we need to change 10 squared to the 3rd power, which means we need to times 10 to the 6th power. So finally we make it like times 10 to the 3rd power. Okay, so this number is nothing but 8.49 times 10 to the 28. So this is atom per volume. So the SI unit is meter per meter cube, or meter to the minus 3rd power. Okay, so finally we can just make use of J equals NE times VD. Okay, and of course we would like to use it as VD equals J over NE. So J is actually this one. This is I, but I will be I times D. So or maybe I times I over A. J equals I over A. So it will be like I over NEA. A is the cross-section area because it is just a cylinder. So, and this is the radius. We can just calculate the cross-section area. So finally, we can just plug in all the number. I is 17 times 10 to minus 3rd power, and then N is actually this number. This is N. Maybe I just go to the next row. So go to here. So it is 17 times 10 to minus 3rd power, and then this is 8.49 times 10 to 28th power. And then E is 1.6 times 10 to minus 19, and then times pi r squared, pi, and then r is 900 times 10 to minus 6 power, and then quantity square. Okay, so just need to and use a calculator to find the values, which would be 4.9 times 10 to minus 7 meter per second. Okay, so it is very, very slow. So this is meter per second, but this is a 10 to minus 7. We don't need to care about 4.9 or 6.9 or whatever. So 10 to minus 6 meter per second is really, really slow. You can simply imagine. But yeah, so which means that if I just try to switch on or switch off the light, actually the electron is moving such a low speed. It's slower than a snail. But yeah, how does it work? How does it work? Because if I try to switch on or switch off, it's just like the light will turn on or turn off instantly. So the idea is that actually the current or the electron are like a 5-volt or like yeah, actually they just push the current going forward, just like it's just like for example, this is a switch. For example, this is the lamp. This is the lamp, and then this is the current. Okay, actually the current, or maybe this is a battery. Maybe this is a battery. So imagine this is the electron going this way. The electron going this way. So actually the electrons are really that slow, but throughout the loop there are many current, which means that if I try to switch on the light, all the current are going in a very slow speed. So actually the current right in front the lights will go in and then consumed by the light, so you can see the light is turning on. So it doesn't necessary that the electron directly go from the switch to the light to turn on the light. It only need to push the electron inside the loop forward, so that it can consume the energy. Okay, so let's stop here today, and I will see you on Thursday.